Hello, everybody, and welcome to the Astro Show, the place to be if you're curious about the cosmos. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brains of astrophysicists, get advice from an aerospace doctor, learn about what astronomers have to say about life, and find out about what's going on up above your head, all in the same place. So please join us the second and fourth Tuesdays of every month at 6 p.m. Mountain Time on Twitch, YouTube, and Facebook. You can chat your questions on Twitch and YouTube, and we would love to hear from you. So ask questions, make some comments, and we will respond to them during the show. In this week's show, we are going to chat with Dr. Hiawan Mao, an assistant professor of physics and astronomy at the University of Utah. Among other things, Yao studies the nature of dark matter and galaxy formation physics. We will hear all about that later on this evening, but before we get to that, let's welcome our co-stars. First, astronomer and data visualization engineer at the Adler Planetarium, it's Dr. Lauren Corlees.
Hey, Sam, good to see you.
Hey, Lauren, good to see you as well. Next, author, journalist, and creator of the Space Tourism Guide, it's Valerie Stymick.
Thanks so much for having me. Glad to be back.
Yeah, glad to have you, Valerie. And we've got a couple other folks who may be joining us later. We're not sure. Dr. Nick Galitsky and Dr. Danny Carroll. We hope that they join us at some point later on. And if they do, we'll let them on the show. But until then, it's going to be the three of us and then our special guest when we get there. So on the show for tonight, we're going to talk about galaxy formation and dark matter with our guest star, Geminid meteor shower, and some gamma ray bursts. And that's a bit of a spoiler for the news quiz. So hang on to that one, co-stars. That's a hint there for you. All right. Well, we are going to get started off, as we always do, with Astro Advice. Life advice from astronomers, astronauts, and other scientists. So I'll read the quotation, give you the options of who actually said this, and the co-stars will give their best guess in who they actually think said this lovely tidbit. So, I'm a true believer in the strength of teamwork, in the power of dreams, and in the absolute necessity of a support structure. So, 4 possibilities. One is Nobel laureate, Dr. Jim Peebles, Canadian-American astronomer, I should add. 2, Jainat Ralinkar, also an Indian astronomer. 3, Julie Payette, who was a Canadian astronaut and actually the former Governor General of Canada. We almost had her come and speak at our science speaker series back in the day, but the timing didn't work out. But she has a lovely staff who was very, very excited to work with us. And D, Amy Mainzer, who's also an American astronomer and has done all kinds of really cool stuff with astronomy education. So those are your 4 options: Jim Peebles, Jainat Ralinkar, Julie Payette, and Amy Mainzer. So, co-stars, what are you thinking?
I was going to guess C, Julie Payette.
Okay, we got 1 vote for Julie Payette.
Okay, I'm going to go with A, Dr. Peebles.
Dr. Peebles. Okay, 1 vote for A, Dr. Peebles, and 1 vote for Julie Payette. And I forgot to mention, Julie Payette is also an engineer. So a lot of exploits to her name. The correct answer was Julie Payette.
Hey.
Nicely done.
Thank you.
That is 1 point for Lauren. All right.
The points have already started.
They've already started. So nice work, Lauren. And now I'm curious what the two of you actually think about this quotation.
Yeah, I mean, I think particularly over the last few years of the pandemic, we've all become really aware of needing a support structure. That like you sort of had that from your living your life, and then when we all went inside, and now we're coming back out. But I've been really, you got to be a lot more purposeful in cultivating that kind of a structure, and just for me personally, recognizing how much I really do need it. It's like how, I don't know. I've been appreciating mine more lately than I would have done maybe in the past.
Likewise. Yeah, well said, Lauren.
What I really liked is that all 4 people that you gave as options had accomplished things in their lives through which teamwork and support structure and dreaming would have applied. So I have a feeling that none of the options would have had any disagreement with this as a statement that to where they got in their careers.
Yeah, absolutely. Without a doubt. Yeah, I mean, it's hard to find anything wrong with this one. We've definitely had some controversial quotations over the Astro shows. This one is not one of those.
Yeah, but I like that it like goes against this idea that there's like a genius scientist who goes off and does all of this work. Like that's just not how it works. And like figuring that out even really early on as an undergrad to be like, no, the only reason we all got through the major we were in was by doing all of our homework together and conversation and helping each other understand what we were doing. That just continues on as you keep doing this kind of thing. So.
Yeah. Lauren, that just brought me back to high school when my buddies and I would all gather around the same table in the lunchroom before school and finish our calculus homework together.
Yeah, like we all have those experiences and it makes it fun. It's like, I don't know. I had a lot of them in college and I really enjoyed it.
Yeah, in college as well. I mean, I remember study groups and I was a TA for a couple of physics classes, and I just had like office hours in like the hallway in the science building, and people could come in and like sometimes they would come up problems that I couldn't solve by myself, but like the two of us could figure it out. And so, yeah, I mean, and then there's of course like, you know, like spell check and grammar check on Microsoft Word. I don't think I would have got through my PhD without that. So that's
a support structure right there.
Yeah, it's way more than just people, right? There are lots of things that that help us do the things we really want to do to achieve our dreams. But yeah, definitely the way we form support structures with people is probably by far and away what supports us the most over the years.
And vastly underestimated. I think we see a lot of pop culture and a lot of even like social media that looks toward the individual accomplishments and the people who've done that. And it's, you know, there are some people who are truly exceptional and accomplish a lot on their own, but the rest of us, that's how we all get along and get ahead as we work together and we lift each other up.
Yeah, and I would say even with those cases where it seems like somebody may have achieved something in isolation, I kind of doubt that it actually happens that way. I am under the impression that there is really no isolation. Nothing exists independently from everything else. So, I mean, like, do those people actually build their own cars, or you know, like all the things, right, that we rely on from other people in our lives? Like, none of us are independent.
I think about all the cafeteria workers in every school who are like unsung heroes, keeping people doing hard academic work well fed and their brains working with good calorie intake. You know, those people never get any credit in the movies.
I would not have survived high school without those French toast sticks in the cafeteria in the morning. I absolutely loved those things. So yeah, and it's everybody. It's, you know, the people who pick up our garbage, to the people who design the computer chips that go into internet systems all over the world. So Julie Payette, you nailed it on this one. Nicely done. And at some point, we'd love to have you as a special guest on the Astro Show. If you happen to watch this recording, we would love to have you. All right. So let's move on to Astro 365. So on this day in 1920, Francis G. Pease made the first U.S. measurement of the size of a fixed star. Happened to be Betelgeuse, and he measured it to be about 260 million miles in diameter, making it about 150 times larger than the sun, which is big. It turns out Betelgeuse is actually way, way bigger than that. The actual known size of Betelgeuse is 767 million miles in diameter, which makes it one of the largest stars in the Milky Way galaxy. Not the largest. There are some that are bigger, but it is definitely one of the biggest. The biggest ones have a diameter of just over 1 billion miles in diameter. So those are really, really big stars. And the reason those stars are so big, and we call them red supergiants, by the way, because they really are supergiants, and they appear red in color. The reason they appear red in color is because they are cooling off. If you think of your gas stove, when you've got a really good flame going, it's kind of that greenish blue color. But if you happen to like spill some water that you're boiling onto it, it kind of flashes red or orange when the flame cools down. And that's what's going on. These stars are exhausting the majority of their hydrogen fuel. And so they are cooling off and expanding outwards. So they get really big and cool relative to other stars in the sky. So when you see those orangish or reddish stars in the sky, those are the really, really big, cool ones that are nearing the end of their existence. They're not necessarily the oldest stars, because very, very large stars actually burn through their fuel more rapidly because they've got a bigger force of gravity crushing down on them. So they exhaust their fuel in millions of years, as opposed to billions of years with stars like the sun that are quite a bit smaller than that, which will never get as big as Betelgeuse, even when the sun begins to run out of its hydrogen fuel, and will puff out, but nothing like Betelgeuse. Oh, and by the way, we get these really, really big stars exploding, which we call supernovae, about once every 50 years per galaxy somewhere in the universe. And in the Milky Way, that happened about 400 years ago. So we are due. And if there is a star that's going to explode in the next 50 years, it might just be Betelgeuse. So when will it actually happen? We don't know. But what we can say is that it will happen sometime soon. It could be tomorrow or 100,000 years from now. We don't really know, but somewhere in that time frame. So this time of year, Betelgeuse is up in the sky. It's the left shoulder of Orion when you're looking at Orion up in the sky, and it will get really bright when it blows. It'll be as bright as the full moon for a little while. So it'll be quite a show indeed. Hoping that happens in my lifetime. All right, well, that's what happened today in 1920 on December 13th. Now it is time for the astronomy news trivia game. Co-stars, are you ready for this?
Yeah.
Right, yeah, there's some enthusiasm. I love it. All right, so we've got
opting for enthusiasm instead of anxiety.
Good. That's what we want. This is supposed to be fun. Remember, it does not go into your H index, so it's no worries. Okay, so Lauren, you are up first, and then Valerie, and then the questions that we had for Nick. Oh, we got Nick. Nick, I didn't even see you there. Nick, hello.
Hey, sorry I'm late.
Dr. Nick, welcome. I'm sorry, man. How long have you been sitting there?
Oh, just 30 seconds.
Oh, perfect. All right. Well, we are psyched to have you. And that means we're only going to do 3 questions in the lightning round. We for news trivia. So you're right on time.
All right.
Okay. All right. So Lauren first, and then Valerie, and then Nick. Here we go. Lauren, first question. A new study changed the way astronomers think about gamma ray bursts, because for the first time ever, a long gamma ray burst was observed from what?
I don't know. I didn't hear about this one.
So think about where you normally see short gamma ray bursts from, and this is where this long gamma ray burst came from.
I still don't know. Yeah, I'm revealing how little I know about gamma ray
So
bursts.
here, you want a hint?
Sure.
So we just talked about supernova.
Yeah.
This is even bigger.
And a supernova?
Yeah. It's one of these lovely little fancy terms that astronomers make when they find something bigger in the category of where they thought was an upper limit. So it's not super, but it's
Mega. I don't actually know.
Yeah, you're so close. It's not a meganova, but a
Giganova?
You're so close. It's kilonova.
Kilonova.
Yeah. So the first ever long gamma ray burst was observed from a kilonova. So this happens, we think, from merging neutron stars, and up until now, kilonovas or merging neutron stars only produced short gamma ray bursts. But this was a long one, and so astronomers really don't know why this happened. Theory does not predict it, so they're going to have to formulate some new theory, which is pretty cool. Love the way science works like that.
Also, our band is now called Kilonova, okay? That's such a cool name.
That is the new name of the band, Kilonovas. Yeah, I actually think there are Kilonovas. I think that is a real band out there somewhere. Yeah. All right, here we go. Question number 2. What was blocking the Peekaboo Galaxy from view until relatively recently, and why are astronomers excited to study this galaxy? This is not a trick question, by the way. There was indeed something blocking this galaxy from view. It's way simpler than you might be making it out to be. Like what could possibly block a galaxy from our perspective?
Another galaxy?
Or potentially something more local? Something really close to us compared to the galaxy. In the Milky Way.
A star, a planet.
A star, you got it. Yeah, it was just a fast-moving foreground star.
Oh, cool.
And sometime in the last 30 years or so, 40 years, it finally moved out of the way. And astronomers are able to image this galaxy that they're calling the Peekaboo Galaxy because it peekaboo from behind the star. And the interesting thing about this galaxy is that it's this weird looking dwarf galaxy, and there are a very large number of young stars and almost no really ancient stars, and it doesn't fit with other galaxies at its distance. So for some reason, the makeup of this galaxy is pretty strange. Astronomers don't know why that the color temperature profile of the galaxy doesn't match other such irregular galaxies out at the same distance. So a bit of a mystery on that as well. All right, third question for you, Lauren. Astronomers using the recently named Margaret Burbage Space Telescope, remember that from last time? That's what we're calling the other telescope, named after the NASA administrator who wasn't such an awesome leader, according to us. So that space telescope just confirmed the oldest group of what?
Galaxies?
Galaxies.
Hey, that one I knew.
Yeah. Really old galaxies.
Yeah.
The redshift on these puts them at about 13 points. I can't read it on the screen there. Over 13 billion light years away. So they are like we are seeing them just like a half a billion years after the formation of this universe, which is pretty remarkable. So yeah, the most distant galaxies ever seen.
It's also exciting because this is one of the key things that the telescope was supposed to do. And so to have like that be one of the first new big results, like it's actually doing the science we designed it for, is incredible. So,
it is pretty awesome.
Yeah.
All right, so Lauren, you got 2 out of 3 there. And you already had 1 point, so that brings you up to 3 points. So Valerie and Nick, you each need 3 points to tie. And then the lightning round will decide the champion this week. Okay, Valerie, are you ready?
As I'll ever be.
All right. A recent study found that the second coldest blank to host planets also has the second most favorable, here's a huge hint, HZ blank orbiting around it.
Well, it would be a hint if I knew what HZ was. So I have to get both parts, though. This is like one of those. To get the full point, I have to get both of the blanks. So
something has got host planets. What has that got to be?
Well, it's got to be a star. So
That's got to be a star. Okay, so you got half of it. There you go. Yep. And
it also has the second most favorable. Oh, it's habitation zone. I got there. Okay, but I don't know what comes after that. Yeah. So you're right. It's a planet in the habitable zone. What type of planet in the habitable zone is raising such a stir about? Well, I don't know if this is a term, but I would say Earth-like. I don't know if there's an official term for that.
We're going to give it to you. A terrestrial, yeah. So it's a terrestrial super Earth, to be specific. So this is a planet that we think is terrestrial, but much, much larger than Earth, maybe more like the size of Neptune, actually. But it is orbiting ridiculously close to this star, but that's okay because this star is really, really cold. It's one of these tiny little red dwarf stars. And astronomers are excited because this planet, this terrestrial super Earth, is now the second, the number 2 exosolar planet believed to be habitable in like the long list of like which planets might actually be habitable. There's only one planet in the Kepler systems that might have a higher probability of being habitable. So this one is pretty cool.
Very cool.
And here's the breakdown of where this one falls out with all the other exosolar planets. So yeah, the Kepler planets are down there at the bottom. And then here are all the other planets that have been found, the Jupiter-sized planets, which are way easier to find because they block more of their star's light. The super Earth Neptunes and the Earth-sized planets. So yeah, these 2 in question are right here in the habitable zone. One of them right on the threshold, but one of them nicely in the habitable zone. So yeah, astronomers are excited about this one recently discovered. All right, nice work, Valerie. You got that one. You ready for your next question?
Sure.
All right, here we go. New evidence suggests that a deep underground blank on Mars is causing an area roughly the size of the continental US to bulge upwards, challenging the previously held belief that Mars is geologically dead.
I haven't heard about this, but this sounds so cool. Is it a volcano?
Yeah, it's magma.
That's so cool.
Yeah, astronomers think that there may be a huge magma plume under the surface of Mars, not unlike the huge magma plume under Yellowstone, that is causing this enormous bulge on the Martian surface. We didn't think this was possible, but now the evidence supports such a deal, which is pretty wild. And it's enormous, like the size of the continental United States, this gigantic magma plume. So
I feel like this week's questions are all about all the things we don't know. Whole bunch of challenges to what we assume we know.
Isn't that great? It just took a week for astronomers to announce all this stuff. It's so cool. They just like pulled it out of a hat. Now this is research been going on for a very long time, just culminating in papers this week. Okay, so 2 for 2, Valerie. Nice work. Third question. Although scientists have long thought that meteorites might have brought amino acids to Earth, a new study suggests that the meteorites being bombarded by what might have led to the formation of amino acids in meteorites in the first place.
Okay, I don't know.
This was the hint that I gave at the very beginning.
Oh, we all have questions about this. Well, I'm going to go with gamma rays then.
It's gamma rays. Yeah. Astronomers think that that gamma rays, early on in the formation of the solar system, may have bombarded these meteorites. And those gamma rays can actually cause the decay of certain elements in these meteors to actually form amino acids. So that now is a leading theory about how, if meteorites did bring amino acids to Earth, this is how the amino acids got formed in the meteorites in the first place.
So amino acids might just be teeny tiny little hulks riding around on meteorites.
Exactly.
Cool.
Green. Yeah. Nicely done. A 3 for 3, Valerie. You are tied with Lauren. Nick, big pressure, Nick.
Yeah, I don't know.
One of your answers is going to be gamma rays. Just hold out for it.
No, it's not going to be. No. All right, so we got to skip ahead from Danny's questions here, and we're going to go to Nick's 3 questions. Let's see here. Let's see. That was one of them. 2. All right, so I think, Nick, this is your first question. All right, here we go. A new paper by Nobel laureate Adam Rees suggests that what mysterious energy that no longer exists might be a solution to the Hubble tension in cosmology.
Is that called like early dark energy or something like that?
Got it. Nicely done, sir. Wow, not a moment hesitation. This is bizarre stuff. But it turns out there are these problems with how we measure the Hubble constant depending on what method we use. And there's this discrepancy that hasn't been resolved yet. Dr. Adam Rees has an idea. If you introduce this new type of energy that existed in the early universe that doesn't exist anymore, it may actually solve the discrepancy. We're not sure if this is actually what's actually happening or not, but it's a possibility.
Yeah, I've read some papers on it, and it's as with many things, we have a lot of great observational evidence, so it's really hard for the theories to actually introduce a new thing and still match everything that was observed. But this is one of the contenders to solve this. It's very exciting right now. So
it is, yeah. I mean, I would be psyched if we had another energy to throw into the mix. At least,
another dark thing that we don't know anything about.
Yeah. So the pie of what we know about the universe becomes a whole lot smaller for the wedge we do know. Yeah. Yeah. I like pie. It's all good. All right. Second question, Nick. Earlier this month, the Southern Hemisphere's largest radio telescope, called Meerkat, kicked off its search for what?
I know Meerkat. I've
seen
that data.
Yeah,
it does a lot of different things. What is it searching for?
Yeah, just started earlier this month.
Like, God, I'm gonna embarrass myself because I really should know more about that telescope.
No.
This
one won't embarrass you at all. Actually,
I forgot about kilonova. Don't worry, you're fine.
There you go.
Kilonova. This one is not exactly in your wheelhouse of what you research. It's kind of far out.
I'm gonna say reionization because I think it's kind of looking for that, but I could be wrong.
I think it has actually done research in reionization. No, this is more a little out there. This is one of the coolest things that Meerkat is being used for. It is it's part of the Breakthrough Listen program, and they are searching for technosignatures for extraterrestrial
SETI fun.
Yeah.
There you go. When in doubt, it's aliens.
I know.
Gamma rays are aliens.
Gamma rays are aliens. Yeah, something like that. Okay, we can't give you that one, Nick, but you can still come back in the lightning round. Okay, a new multi-kilowatt laser system was recently developed by NASA for what purpose?
Laser system. NASA. They're not getting in on the fusion game. I'm going solar cells or something like.
Go back to the previous question.
Aliens?
Not aliens, but something that has to do with potentially what with aliens?
Space communication?
Space communication. You got it. Yeah.
Alright.
Deep space optical communications with lasers.
Ooh,
Yeah, pretty cool stuff. And it's actually going to be tested.
there you go.
Yeah, there's a space probe out there that's going to do some tests. So it's pretty cool stuff.
Want that 5G bandwidth out by Mars?
Yeah, right. Not bad. Nick, you got 2 out of 3. So you got to pick up one more in the lightning round to tie. 3 more questions possible. And let's see, they begin with this question right here. So co-stars, all you got to do is just say the correct answer as soon as you think you know it. All right. Are you ready for this? Here we go. SpaceX just launched Starshield. Instead of providing internet services to end users and businesses like Starlink, Starshield's customers will be... Who will they
Government?
be? They are governments. Yes. These satellites are specifically for intelligence type operations and national security. So we don't know what Starlink is going to be doing with these satellites, but they are going to be offered to businesses. Yeah. Nicely done, Valerie. 4 points for Valerie. Next question.
I know this one too.
What the Japanese billionaire Yusaka Maezawa announced last week? Valerie, I think it's all you.
A highly unrepresentative group of people who will be going on the Dear Moon project. But yeah, the Dear Moon participants.
The Dear Moon crew. Yep, it is true.
It's actually, I shouldn't be too harsh. It's wonderfully representative of the world in terms of the nationalities.
Yes.
It's just not great in other parts of the representation spectrum. So.
Indeed. But nice work, Valerie. You're up to 5 points now. Wow. I think that makes you the champion, but we do have one more question, and then we've got to get to our special guest. So let's do this here. Last question. Collins Aerospace was just selected by NASA to develop what?
Aliens.
Gamma rays.
Mars lander? I'll just
no, more local, way local. Very, very local.
Taco truck.
less local. They are developing the next generation spacesuit for extravehicular spacewalks on the ISS. Yeah. So Valerie, you crushed it. Nicely done. 5 points for Valerie today. I am very impressed. Nicely done. You are a champion. All right, we might get to What's Up, Dr. Sam later on, but we need to bring on our special guest. The What's Up, Dr. Sam tonight is a Geminid meteor shower. So if you're somewhere where there are clear skies tonight, get out before the moon comes up. The moon comes up at about 11 p.m. tonight, or 10 p.m. tonight. So if you get out before the moon, you will have a chance to see the Geminid meteor showers. It should be really good. Optimal time is like 2 a.m., but the moon will be too bright. So get out early, check out the Geminid meteor shower. And with that, we are going to bring on our special guest and have some fun chatting with Dr. Qiaowan Mao. Yao, thank you so much for being with us today.
Hi, everyone. Great to see you. Happy to join you.
Yeah, we're psyched to have you. Well, we'd like to start off these guest spots with the same question. So what's the one question that you wish everybody would ask you, but nobody ever does?
Yeah, so the question, well, I mean, to be fair, I guess I wouldn't ask other people this question too. But a question that I hope the other people will ask me is, what units of length do I use most often when I'm at work? And this question is interesting because astronomers happen to be one of the few professions which, when you say what other unit that you use, that people can tell your profession. There are a few other professions that have the same similar characteristic, but astronomer being one of those. And you can even sometimes tell what specific subjects that astronomers studying by the answer of the unit of length that they use.
Very nice. And so the answer to that question, if I were to ask you that, would be?
Yeah, so for me, I would use megaparsec. And so megaparsec, it means a million parsec, and parsec is the distance for something that when you look on the sky, they have 1 arcsecond separation. And in the physical distance, it's a 1 astronomical unit. So that distance between the Earth and the Sun. So basically, if you are an alien looking at the Earth and the Sun, and the Earth and the Sun happen to be separated by 1 arcsecond in the view of the sky, then the distance of the solar system to that alien would be 1 parsec. And that is, if in terms of miles, that's about 20 trillion miles. In terms of light year, that's about 3.25 light years.
I think your explanation of what a parsec is, using aliens looking back at the Earth, that is the best definition of a parsec I have ever heard, a megaparsec. Thank you for that. I hope that you publish that somewhere. That is brilliant.
Thank you. Right, but that is a parsec, and the unit I use most often is a megaparsec, which is about like a million. Not about. It's exactly a million parsec.
Yeah.
And so that is really big. That is like, well, I guess a million, so 10 millions of trillions of miles. For scale, like our galaxy, our own Milky Way galaxy, the diameter is about 40 kiloparsec, so 0.04 megaparsec. And so really at megaparsec scale, galaxies they look like a dot. And so a lot of the study about like large scale structure where we use the unit of megaparsec, we literally treat galaxies as like single points. And we don't care about the structure of the galaxy. We don't care about individual stars. We are looking at the distribution of the galaxies, how they're scattered in the universe, and understanding the pattern of the galaxies that that formed within the universe. And so it's kind of it's just a humbling unit to be using. Thinking about how that scale really, like how, well, to some extent, when you look at that scale, all the scale that we use in our daily life kind of become irrelevant. And so that is kind of a very, like sometimes when I kind of pause and realizing that is a very interesting kind of reflection.
I love that. I think I'm going to start asking that question that you came up with when I meet people of different professions. What unit of length do you use in your profession? I like that. Nice. So how did you get into studying the distribution of galaxies?
I mean, for me, it's mostly just a luck, I guess. When I went into grad school, I wanted to do high energy particle physics kind of stuff. But at the first year, as a first year grad student, you just kind of need to find a research advisor who kind of have a spot open. And that's when I met my PhD advisor, and she was doing like cosmology, documented stuff. I know nothing about that. But luckily in our graduate program, we have this rotation program so you kind of work with the advisor for just a short period of time to see if you are interested in the research topic, if the personality matches and things like that. And so I was like, yeah, sure. I mean, I don't have any advisor at this point, so I'll just work on this thing that I have no idea about, dark matter. And it turns out it's super fun. And I work well with my advisor, and so we kind of just start to learn everything about the evolution of the universe, about how dark matter really connected to the formation of galaxies. And that kind of just become, what I did for my PhD and stepping on this career, I guess, since then. Nice.
Yeah, I think a lot of people share similar stories of how they got into their.
No, I mean, a lot of people have I have a telescope when I was a kid.
Okay, that's the stuff we really want to hear about. How did you really get into this? Yeah.
Yeah. So, but for me, it's really luck, just pure luck to some extent.
But you had a telescope when you were a kid. What kind of telescope do you remember?
No. I say I don't have a telescope as a kid. I'm just saying a lot of people said that. I don't have a telescope as a kid. I wasn't meant to be an astronomer, I guess. But yeah, but it is where I am now.
Okay, so if you weren't meant to be an astronomer, what did you think you were going to be?
Well, I guess at one point in life, I've been trying to become either a web developers or like a software engineer. Like I actually really love doing websites. I like a lot of during my hobby time. I build websites for no reasons, and it's just a thing of pickup. I guess a little bit nerdy, and yeah. So I guess I've been thinking doing that as my profession. But sometimes things are more fun when it's a habit. So maybe it's good in that sense.
Yeah. Sometimes it's best to keep the things you're most passionate about as hobbies. So tell us a little bit more about what you study. We've got some pictures I can bring up if you'd like, but I know everyone is always interested in like aliens, black holes, and dark matter. Like that's what everybody wants to talk about. Like when we do stargazing programs, and you've got one of those three like under your belt. So tell us about dark matter and how that works into your research.
Yeah. Do you want to show? You want to bring out some of the pictures?
Yeah. I'll bring that back up for us. Oh, sorry. I wanted to do this one so you can see everybody.
Yeah. If you just flip one before this one.
Oh, before that one. Sorry.
Yeah. Just want to give a little bit of context. So this is the picture of a night sky from the southern hemisphere. Unfortunately, here, if you are in the northern hemisphere, you can't really see the large and small magnetic clouds. But on the right, that is our own Milky Way galaxy. We are sitting about 8 kiloparsec away from the center of the galaxy. And then on the left, these two small blobs are, we call that satellite galaxies. It's called satellite galaxy because it's orbiting our galaxy. So it's like a satellite orbiting some other thing. But there are also galaxies that are just much smaller galaxy compared to our own Milky Way, as you can see from this picture. And if you go to the next one, this shows is kind of put that picture into perspective as you kind of sitting outside looking at the Milky Way. The Milky Way is sitting at the lower right. If you look very closely, you also show the LMC and SNC, the large and small magnetic clouds there. But there are lots of other satellite galaxies that are orbiting the Milky Way, not just these two. Today, we have already identified about 60 satellite galaxies that are orbiting the Milky Way. And this is also not unique to our own Milky Way. So on the left, you can see the Andromeda galaxy, M31. That is the closest Milky Way-sized galaxy to us. And you can see a bunch of other smaller galaxies also orbiting the M31 as well. So whenever you see this kind of a large Milky Way-ish galaxies, you always discover satellite galaxies that are orbiting them. And so you might ask, why that is the case? Is that a coincidence? Why don't these galaxies just kind of randomly distribute in the universe? Why do they clusters in this kind of features? And if you go down to the next slide, which brings to, I guess, what you say everyone wants to hear about, the dark matter. So the reason that we have this structure in the universe is really the underlying distribution of the dark matter. So dark matter is something that we believe exists in the universe for various different reasons. But one of them is the discovery of this, satellite galaxy systems or galaxy clusters. And here you can see kind of the filamentary structure is we call it cosmic web. It's basically how the dark matter is forming the structure of the building block of the universe. When you see the bright spots on this figure, the yellowish spots, those are the locations which we think the galaxy will form. And so you can kind of see there are very large yellowish bright spot, and then there are kind of smaller yellowish bright spot around it. And those are the structure that we are seeing just on the previous slide, which you have a Milky Way galaxy, and you have a bunch of satellite galaxies orbiting them. And so it is actually because the structure of the dark matter that we can see the pattern of the galaxies as we see today in the real universe.
Very cool. Yeah, I've seen images like this before, and it's just mesmerizing to think about the size scale that we are looking at here. Like you were saying before, where each galaxy basically just becomes a point.
Yeah, totally. I mean, so if you let me think. I think the width of this picture would be around. I don't know the exact number, but roughly speaking, this would be about like 300 to 500 megaparsec.
Wow.
Right. So because like the Milky Way galaxy itself is only like the galaxy itself is only 20 kiloparsec. The system with all the satellite galaxy, if you take into account, that is only about 300 kiloparsec. And that whole thing will only fit into one of this small corner on this picture.
Wow. Very cool.
Yeah. And actually, if you go to the next slide, I kind of highlight that kind of how that would kind of fit in that picture. And so you can see the Milky Way size system is the one that I highlight on the kind of upper middle. And that is really small compared to a galaxy cluster, which is about like 3 to 4 times in size, in diameter. And something in between we usually call it galaxy group, but this is just like kind of different sizes of this kind of satellite systems. It's all similar. It's just like smaller galaxy orbiting larger galaxies. It does look different, like observationally for galaxy cluster. In order for galaxy cluster to like become this big, all the galaxy must form at much earlier time, so that they have time to kind of merge and they become this kind of super large groups. And so if you look at a galaxy cluster, you usually see like redder galaxies because they have formed earlier in the universe and they just like kind of travel until they merge into a large cluster. For the Milky Way size system, it's because it's smaller, so it doesn't need to take that long to form. And so the galaxy can be younger in that sense. And so sometimes you see a bluer galaxy in Milky Way satellites. And that is kind of the reason, because that have different colors actually due to the formation time. And that is, again, being controlled by the dark matter. So a lot of my study is really trying to understand the connection between dark matter and the galaxies that it forms. And then that the other side of this slide is just showing you kind of the scale. So the Milky Way systems, if I zoom in, I can see all this different density peak of the dark matter. And the Milky Way galaxy really only sit at the very center of this dark matter structure. Right? Again, I mentioned the size, the Milky Way size is only about 20 kiloparsec, which is about only 1/10 of that system itself. So yeah, very different scale. But it's very interesting to see what kind of galaxy would live in what kind of dark matter. We have this jargon that we call this structure a dark matter halo, which are kind of visualized in the lower right. And so understanding the connection between galaxies and their hosting dark matter halo is kind of what I have been studying and trying to understand why a specific kind of galaxy will form in a specific kind of dark matter halo. What their relationship, do they evolve with each other? Does the galaxy impact the formation of the halos? All these are the questions that I'm interested in answering.
Is this part of trying to resolve and this is not my specialty, but trying to resolve the missing dwarf issue?
Yeah. So those things, there are several, like the one that you just mentioned, the missing satellite problems. There is a set of problems. Nowadays, we call them the small scale challenges. You might have heard of missing satellite problem. You might have heard people say like too big to fail problem. If I've been following astronomy literature, you might have heard the satellite plan problem. That is kind of the most recent one. You might have even heard an older one called cosmic core problem. But all these problems is kind of related to how galaxies connect to the underlying dark matter halos. And I guess there are more problems now because we actually understand more. So like in like you say, like there was missing satellite problem, and people say, oh, it's actually not a problem once you understand these things. And then people say, oh, but then once you put those in, then you have this additional problem. And then we say, oh, but then we now understand this thing. And then people say, oh, then but there's problem 3 once you fix all these things. So yes, there are endless problems to solve. but really it's kind of like how we understand, it is kind of connected to how we understand the connection between galaxies and the host halos that they live in.
I guess which angle are you going at it, Eth? Are you on the observational side, the theory side, or simulations, or?
Yeah, so I mean, I have been shifting a lot. So when I was a grad student, mostly doing simulation, and so like the image that you shown, this particular simulation I didn't run, but like I ran a bunch of similar simulations, and then I kind of go into the theory of like, when I say the connection between galaxy and halos, kind of actually develop a series to connect the halos and the galaxy they're hosting, and so like kind of like trying to write out the actual theory that connect those things. But in the past, I would say maybe 6 to 7 years, I kind of have switched to a more observational side. So nowadays, I'm like trying to find those dwarf galaxies. So this smaller galaxy that you see living in these subhalos, or what we call a satellite galaxy, they are difficult to find, mostly just because they are faint, right? Really faint, intrinsically faint, and so difficult to identify in the vast universe. And so I've been very interested in like, how do we identify them? And that ranging from, using, another very cool thing about astronomy recent days is that we now have a lot of astronomical surveys. So instead of like, people have telescope, I mean, people still do that, but like instead of like having telescope look at individual objects, we build large telescopes that just look at a large portion of the sky. And then all astronomers can use those data to study the things they are interested in. And so one particular thing I'm interested in is that if we have this very large astronomical surveys, how do we identify these very tiny small dwarf galaxies from those surveys? And I have been working with some of the existing astronomical surveys. One specific one is the DESI Legacy Imaging Survey. So this is actually an imaging survey that was used for a survey that is used for study dark energy, called the Dark Energy Spectroscopy Instrument. But then I'm also preparing for, I think many of you might have known, the upcoming Rubin Observatory, the Legacy Survey of Space and Time. And it's an upcoming survey, but like this is going to be really impressive data sets. So impressive that we are so scared that we are not prepared when the data arrive in about 2 years. We're just like, what are we doing right now? And so there's just a lot of work that gone into like preparation, like making sure we understand what kind of data we will receive, making sure that we understand data quality, understand we have the analysis pipeline that is needed to analyze those data. And so that is super fun. A lot of work going into that. But the LSST is going to discover like millions of dwarf galaxies. And so I'm really excited and really want to see like what do we need to do in order to understand those galaxies.
Yeah, I was captivated by what you said earlier about how as the astronomical community has learned more about specific interrelationships between galaxies and dark matter, that these problems have seemed to actually grow as opposed to shrink. Do you see an end in sight of all that? Like, will the Vera Rubin telescope or the Margaret Burbage space telescope, as we're calling it, is that going to actually start alleviating some of these so-called problems? Or as we learn more, are we just going to continually create larger and larger gaps with our theory and observations?
Yeah, that's a great question. I wouldn't say that we are actually creating more gaps, but I don't think the problem will end. And I don't think the problem will end not because we don't have great observation or we don't have great theory. I don't think the problem will end because that is the nature of doing science. That the nature of doing science is not just like finding solution. It's actually finding problems. And so that is how science developed. That is, you have a theory, like for example, that we have Newtonian mechanics, right? And then the work of scientists is to find where then that theory would no longer works. And that is really how science progresses, in my opinion. And so we learn more, like even compared to a decade ago, which everyone was discussing missing satellite problems, we know way more about galaxy formation and the connection between galaxy halos. But we do also have more problems. And I think that is because the science actually has made progress. It's actually a sign of that we make progress. Is that now we all understand all those things. And because all this new theory that we put together for the understanding of the galaxy formation, we need to test them in more different regions. And so we have this new test A, B, and C to test all the theory we have developed since the last decade. And so I think we will just have even more problems because with LST, with a wonderful telescope, space telescope, we will just kind of learn a lot more about astronomy. And that would put the existing theory to new tests, creating new problems. And I think that's a good thing.
It is. It's a wonderful thing. Thank you for articulating that so well. That really is the beauty of science.
I do hope we figure out a few things, though. Like, if I'm going to be real disappointed if we don't know what dark matter is by the time I die.
I was going to say, that's the big one we're missing. That would be so helpful.
Yeah, what does it make up, like 20% of what we think exists in the universe? It'd be nice to know what it is.
I remember, I think about 10 years ago, there was a moment where everyone was so excited about we might know what dark matter is very soon. There was a time where LHC, that is before we discovered Higgs at LHC, and everyone's like, we might just discover dark matter from the collider physics. And I remember
we were so young and naive.
I remember that all the conferences were we might just discover dark matter, yes, tomorrow. And then that never happened. And nowadays, LHC just confirmed all the standard model physics. So it's kind of sad that hasn't happened, and we don't know how long it would take for us to figure that out. And I mean, it's also part of why I think as astronomers, so far astronomers mostly think, well, dark matter exists. I mean, it's up to the particle physicists to figure out what they are. But in the past decade, I have kind of changed my mind on that. Astronomers need to do a little bit more work here because, apparently, we're not going to find dark matter with particle physics methods. So we really need to figure out how do we do that with astronomical data sets. And dwarf galaxies is one of the way. There are many other things that people are using to study the nature of dark matter, using strong lensing systems. Look at micro lensing systems, and I'm particularly excited about the Rubin Observatory because it will really provide us so much rich data sets that can be used to study the nature of dark matter.
So do you have a hunch of what it is, Yao?
Yeah, I don't know. I personally feel like the universe is kind of going to, we always hope the universe is going to be simple and elegant, but I feel like universe might be really messy on this one. I feel like it might be a mixture of things, a mixture of different type of dark matter particles. And that is also why it makes things a lot more difficult to pinpoint. And because all this, different property might have contributed to the composition of dark matter. But yeah, we'll see.
I was hoping you were going to give us some more definitive answer, and then we could come back 10 years from now and say, Yao got it right. He knew it back then.
I think most likely we were going to get it wrong anyways.
Well, yeah, we just have a few minutes left, but one of the reasons why you're one of our guests is because over this past year, the Astro Show has hosted guests from the astrophysics out list, and you're the moderator of that list, right?
Yes.
So I would love to hear a bit about the history of that list, how it formed, why it's so important, and I'll just say that next year we're going to do the same thing with the Astro Show. We're going to hope to have all of our guests from the astrophysics out list. This being our last show in 2022, but in 2023 we're hoping to have every single one of our guests from the out list.
Yeah, well, so first of all, thank you so much for inviting your guests from the out list. That was really a great initiative. The out list was actually started a very long time ago. I believe it was started around it started in the 90s. 1993, 1994, around that time. And the time is very different at that time, right? Like being LGBTQ in astronomy is not easy, and it just rely on some of this kind of whisper network to kind of get to know each other. And so there are some institutions that are just like, maybe we can put something. Well, that is also the time which internet started to become a thing. And so people are like, maybe we can put lists on the internet and then kind of let people know about that. And so that is kind of the early history of the outlist. And outlets kind of stay in this kind of very, I would say, if you look at a website, if you go to Google Astro Outlist, you'll find a website, and if you click a history link, it will actually bring to the 90s website design, with all these neon lights, a lot of pink color. It kind of stay in that shape all the way up to like 2018 ish. And I actually mentioned about like the habit of mine is like doing website developing, and so there was once that we were just like, we are looking for someone to help like modernize our website, and we're like, yeah, sign me up, like I'm happy to help with that. So we revamped the website, making modernize it so that you can read it on the phone as well, and that make it a little bit easier for people to sign up, and that really has helped. Like our outlets has grown like maybe 4 to 5 times in terms of number of members in the past few years. And it's continuing growing in a very accelerating rate, like the universe. And so I'm really happy about that. And again, it's kind of just like I was on some of mailing lists, and people are just like, we want someone to do a website. And most astronomers don't do websites. So like I happen to have that skill set and just volunteer myself. But then after becoming a maintainer, I then to realize how important that the outlist actually is. Like I keep hearing about students actually look at the outlist to when they are applying for school to see like whether the atmosphere at the institution are welcoming. The outlist also help people to kind of organize locally, because sometimes you just don't know, like there may be a queer colleague in your department, and you might be at the department for years, and then you will not even know about that. And the Astro outlets really have helped local communities to also connect with each other. But obviously, the Astro outlets does not really change the climate by itself, and that really rely on people still, take on the, I guess, responsibility in a way, and to stand up to all this kind of, all the way from microaggression to actual oppression in our daily life. And if this show happened 2 years ago, I would say things has been gone. There has been improved a lot, and we are moving to a much better place. I don't know. In the past 2 years has been tough for the queer community in a way. Sometimes you sometimes feel like we are walking back. And I think this year is particularly tough for all the transgender community for various reasons. So we have a long way to go. But hopefully, with outlets, with everyone's effort, connecting everyone together, hopefully we will move to a better future.
Well, I think we are moving towards a better future. I'll share a story that just got told to me today, actually, by our operations director. So at our Wyoming Stargazing office in Jackson, we have a pride flag up in a window, like one of those, the big, like full, like size flag ones, like filling one of like our huge 6-foot windows. And we have it up there all year. And so apparently somebody drove by the office today who had just met our operations director, and she called her up and said, I drove by your office and I saw the pride flag, and I was so thrilled to see it because my son is trans, and to know that there are places in the community that are safe is so and so that's exactly why we have that flag up there. So people know it's a safe space. We're part of the LGBTQIA community, and we encourage other businesses to do the same. and people, in your front yards where you live. The more spaces that everybody knows that are safe for the LGBTQA community, the better our entire community is going to be.
Yeah, totally. It's great to hear that. It's actually one thing really wonderful when I moved to Utah. I was, before moving to Utah, I was at New Jersey. And so like, obviously in New Jersey, everyone is cool, but like, I think also part of that, people talk about it less. Like you don't see pride flag when you're walking around in New Jersey, but you see that every day in Salt Lake City. So it's very different. Like there's a stronger counterculture in a way, I guess. And so, but visibility really matters. I think, there are many different types of oppression, and it takes very different form for different people with different identities. And for queer community, one of the difficulties is really the invisibility. Like people don't know that we exist, and so finding way to change that, like what you said about putting up pride flag, is really important, and help a lot with people being able to see the existence of the communities and being able to reach out and connect.
Yeah, agreed. Well, thank you, Yao, so much for sharing all that. I really appreciate it. And thank you for being with us tonight. It's been a lot of fun.
Thank you
we're
so much for inviting me.
Yeah, of course. We'll definitely have you back. And now that you're just in the neighborhood, like just over a couple ranges of mountains over in Utah, we'll definitely have you in Jackson sometime to come hang out. Yeah,
totally. I mean, I get that the neighborhood definition is very different in this area compared to the East Coast. But yes, totally, I would love to visit at some point.
Excellent. Looking forward to it. So we're out of time, but I always like to ask if the special guest has any final words of wisdom or anything else you'd like to say to the folks out there watching right now, or folks who will listen to this recording later on.
For me, or
from you.
Well, I would just say that I guess the people who are in the audience are probably interested in astronomy, and I think studying astronomy is really cool because it kind of put you in a very different perspective, like we discussed, very different length scales. You look at so many different things, and it really sometimes is soothing to think about there are other things they are really such curious compared to our daily life. But being astronomer does not separate us from being human beings, and we are all part of this society and experience everything that's going on in the society. And I think that is kind of an important thing. Like on one hand, astronomy really helped me to kind of reflect on where I am in this society and how at some point irrelevant in a way compared to everything that happened in the universe. But that realization also helped me to kind of connect to actually what, like kind of, re-energize myself so that I can continue to engage in what is going on in our daily life, engage in the society, engage in the community. And so I hope that for everyone who loves astronomy can also do that.
That's awesome. That's fantastic advice. Thank you again for being with us tonight. We've got a thank you gift for you, and our operations director, Maggie, will reach out to you to connect you with that. So thanks again for your time. Really appreciate it. Thanks to all the co-stars. As always, we wouldn't have a show without you. So thank you so much for your time and your expertise that you bring to the show. And to all the folks behind the scenes, our operations director, Wyoming Stargazing Board of Directors, all of our supporters, and all of you watching at home, and those of you watching this recording later on. We wouldn't be here without you either. So thank you so much for tuning in. And we hope you join us next time, which will not be in a couple weeks. It'll be the second Tuesday in January in 2023. So Happy New Year, everybody. I did want to say that even though it looks like there's a Christmas tree behind me, it's actually a solstice tree. I'm I'm a Jewish Buddhist, and all my family is Jewish, so we don't actually celebrate Christmas, but we do have solstice trees, and there's a moose up there as well, so very Jackson-esque right there. But yeah, Happy New Year's, everybody. Happy holidays, and we will see you in the new year. So until then, be well, and don't forget to look up. We'll see you next time. Bye.